Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So actually, I'm going to talk about two things. The first thing, I'm going to give a background about the literature that this paper relates to. This is what we call the expert testing literature. And I'm not going to give a fair background. I'm going to present the background first in a way that fits what I want to say later, and also I will present it in a way that that relates to another paper that I have in this literature, and then I will talk about the paper that I intend to present. This is a joint paper with Tai-Wei Hu, and I will explain how it relates to this literature. So we start with expert testing. An expert provides probabilities of future event. So you can go to the expert shop, ask him for the probability that Obama will be reelected, pay the fee, and the expert will deliver a number between 0 and 1, which is exactly the probability that Obama will be reelected. Or you can ask him for the probability of rain tomorrow, and the expert will provide this number, the number which is the probability of rain tomorrow. So the expert is kind of a fortune teller, right? He provides a product or a service. And the product that the expert provides is probability. And we are paying for this product. And the expert testing literature asks whether we can test the quality of this product or this service that the expert provided. Before I formalize this idea, let me give an example. Suppose that we go to the expert and ask him for the probability of rain tomorrow, and the expert tells us that the probability of rain tomorrow is 100%. Right? Tomorrow, we are going to open the window, and if we don't see rain, we are going back to the expert shop and we demand compensation, right? We clearly got cheated. We got a lousy product from the expert. Right? This is what I will call testable implication. This is something that the expert says which was clearly wrong. Suppose, on the other hand, that we go to the expert shop, ask for the probability of rain tomorrow, pay the fee, the expert check his crystal ball, right, do all his calculation, and provide us the probability of rain tomorrow. The probability of rain tomorrow is 50, exactly 50%, right? Not 48, not 52, exactly 50, right? The expert give a very accurate product. If you go to somebody in the street, you would pay less, but he would tell you that the probability is between 40 and 60. The expert tells you the exact number. Tomorrow, we are going to open the window, and maybe there will be rain, maybe there will not be rain, but we are not going to have a good reason to complain, right? There is no way to show that we got cheated. Right? So in this sense, I will say later that this single prediction about rain tomorrow does not have any testable implication. On the other hand, suppose that day after day after day, for a long run, for many days, we go to the expert shop and ask for the probability of rain tomorrow and pay the fee, and the probability that the expert declares is always 50. Now, in the long run, if we actually see that the frequency of rainy days is 90%, again, it means we got cheated, right? It cannot be. If the probability is 50% every day, then it cannot be that the frequency would be 90%. Then
you have a dumb expert, because he would probably, after a while, update his thing.
Well, I'm going to get to it, but I just want to say that if the expert says 50% every time, it seems that there is some way to check whether he's right, right? In the long run, it seems that there is some way to check that at least some dumb prediction would be we will be able to check whether they are right or wrong. So this is a literature about testable implications of probabilities. I will talk later about how I interpret this literature after I will present the result. But right now, the important thing for me to say is that the subject matter here is the objective probability. I want to check whether the number that the expert gave me is correct. I don't care whether he believes or not or doesn't believe in what he tells me, right? In order to check whether the expert indeed believes that the probability is 50%, we know how to do this. If the expert believes that the probability is 50%, it means that he is indifferent between a bet that will give him $1 if there is rain and a game that will give him $1 if there is no rain. Right? There are very clear implications for subjective probabilities. But this is a literature about objective probability. I want to check whether the expert is right, whether he gives the correct number.
Christian's example is like, so you think that the expert does know the past, right? So,
yeah, I assume that the expert does know the past. Maybe I don't know exactly what you are aiming at, but maybe it will be easier for you to answer it after I will actually formalize a result. OK, so here is what I'm going to do. I'm going to talk about the calibration tests in a way that present them as a formalization of this simple test, observation that I just made, that we can check whether the predicted frequency of rainy days match the realized, the actual observed frequency of rainy days. Then I'm going to present an impossibility result, which will say essentially that there is no way to check whether the expert gives the correct predictions or not. And there are many. I will present one which is taken from my paper, and or actually not exactly. And I will talk a bit about the interpretation of this literature. And this is, I remind you, this is the first half of my talk.
You may get a third of it.
Yeah, it might take more. OK, and I plan not to use the eraser at all, because I don't usually get such a nice whiteboard. So, every day we go to the expert and we ask for a number. And we get a number between 0 and 1, which is supposed to be the probability of rain, right? 1 is rain and 0 is no rain. And every day we actually, so this would be prediction. And every day we actually see what happens, right? 0 is no rain, 1 is rain. This is the outcome. Right? And after many days, the expert says something, we saw what happens. The expert says something, we saw what happens. After many days, we are going to check whether we are being cheated or whether we are getting the correct number. So the very simple example of a way to test that I just suggested, which, as you commented, is not very good way to check, is just to compare the observed frequency of rainy days and the predicted frequency of rainy days. We can say that the expert fails if, in the long run, after many days, right, it turns out that the predicted frequency of rainy days, this is the predicted frequency of rainy days that the expert, according to the expert, if the predicted frequency of rainy days is very far from the observed frequency of rainy days. If this is very far away, we can agree that the expert fails. We can agree in advance with the expert that if this happens, then we have a reason to complain, right? This cannot happen if the expert gives the correct probabilities of. This is what I will call a test. And as I said, if the expert will say 0.5 every day, then it may well be that he's going to fail the test, if the frequency of rainy days will actually be 0.9. However, what? Yeah, however, the expert can still pass this test. I mean, even if he doesn't know anything, the expert can still pass the test. The expert can say, every day he can say just what happened yesterday. Right? If the expert every day say what happened yesterday, he doesn't know anything, but he's still going to pass the test. Right? So this is a very simple example, but it contains the two components of my talk. One is the test, and the other the fact that a charlatan who doesn't know anything about the weather tomorrow can strategically, what we will call, manipulate the test. He can strategically pass the test. But this is a very simple test. A more complicated test is to say that on those days in which the expert predicted low probability for rainy days, on those days, the frequency of rainy days should be low. Right? So let's just formalize this as a more complicated test. Right? I want to say that on those days in which the expert predicted a low probability of rainy days, on those days, the frequency is indeed low. So here is another example of a test. On those days in which the predicted probability is small, I'm only going to go over those days. And on those days, I'm going to give the expert negative point if it actually turns out to be rainy days, and positive points if it was not rain. And if in the long run, the expert collects too many negative points, if this is smaller than, let me try to find this one, I think. If this is smaller than, this is too negative, the expert got too many negative points, right? This means that in the long runs, actually the frequency of rainy days on the days in which he predicted low probability of rainy days, there were more rainy days than non-rainy days. If this happens, then the expert fail, right? We can say that the expert fail if this happens, and similarly, thanks, we will fail him if on the days that he says that there is going to be a rainy day, if on these days there were too many non-rainy days. Right? This is another way of a test, more complicated test. This is a very weak version of what's called the calibration test. And now it's not so obvious that the expert can somehow manipulate the test, right? It is still true that if the expert knows how knows to predict correctly, it is still true that if the expert indeed give you the true probability of rain every day, it is still true that he is not going to fail, or is going to fail with a very low probability. But it's not so clear whether he can manipulate the test, even though he can. Right? This is. So if he says, no, if he says 0.5 every day, if he says, you're right. Now it's not clear. In fact, I don't think there is a kind of a deterministic strategy, but there is still a way to the expert to randomize his prediction. Those of you who know the calibration test, the calibration literature, there is still a way for the expert to randomize his prediction every day and pass the test. And essentially, the expert will randomize. You see that it only depends on, the test depends only on whether the expert says something that is smaller than 0.5 or greater than 0.5. And the expert will randomize between two numbers, one that is smaller than 0.5 and one that is greater than 0.5, according to the performance of each of them, according to how well he managed to how many positive points he accumulated in the past when he predicted this and when he predicted this. So I'm not going to get into this. I'm just going to say that there is a way for the expert to pass the test. And this is a good point for me to relate this literature to the calibration literature that those of you who do machine learning knows. I think the machine learning literature, the calibration, and originally the calibration literature, viewed the fact that there is a way to pass the test as good news, right? There is a way to make good forecasts. Our perspective is somewhat different. Our perspective viewed the fact that you can manipulate the test. Our perspective viewed the fact that there is a way to pass the test even if you don't know the distribution as bad news, right? It means that we cannot distinguish between the true expert that gives us the correct probability and the charlatan that just concoct the probability in this way to just pass the test, right? So there is a difference in perspective here, and I think that the original papers that presented the perspective that I'm talking about today is maybe Lehrer, and one more recent paper that took this perspective and initiated this expert testing literature is a paper by Alvaro Sandroni. But the very fact that there is a way to pass the test was known previously. I think it started with David and Foster Vora. And there are many other papers which you may know.
What if I actually wanted to use an expert? So let's say I sort of will go and...
You want to decide whether to take umbrella.
Well, I actually want to. So assume I can make money on selling umbrellas and I can make money on selling ice cream. And I will ask the expert or the machine learning algorithm, will that actually allow me to make money or not?
No. This will not allow you to make money. I think I will give a better answer later after I give my result. And I will say something about actually using the prediction of the expert to make money or not to make money, to make decisions in your real life. And but no, the answer is no. It will not allow you to make money. Okay. So these were two examples which kind of show you what I'm talking about, right? I will always have a test, and I will always have what I will call manipulating strategy.
The DXK is always IID?
No, I didn't make this assumption of IID-ness. But still, these tests would be, I mean, the expert would pass the test even if it's not IID, and I will comment on an IID in a moment after I will write my definition. So what I'm going to do now, I am here, right? I told you what are the calibration tests. What I'm going to be now is to tell you about impossibility result. And I'm going to formalize the idea of test and the idea of strategy. So for me, a test or a contract, let me call it a test. No, some of these are good. The only problem is that I don't throw away the bad ones. Yeah, thanks. A test would be a set of situations on which the expert failed. So a test would be a test of situations like this, a set of finite sequences, right, of predictions and outcomes, right? So every situation is a finite sequence of predictions and outcomes. And these are situations which, if they happen, this I mean finite sequences of this thing, right? I mean, yeah, this is what I think is denoted like that in a computer. Yeah, so let me denote it like this. Actually, right? So a finite sequences of predictions and outcomes. If one of these situations happens, then we have a legitimate reason to complain, right? And the test, you should think about it as something that was agreed in advance between us and between the expert. And if you think about it, every time you buy a product, then implicitly or explicitly there is an agreement between you and the person who provides the product about situations in which you have legitimate reason to complain, legitimate reason to prove that you got a lousy product and to demand your money back. Right? This is a test. These tests had the nice property that if the expert indeed provides the correct product, provides the correct probability, he will be willing to sign the contract that says that he will have to pay compensation if he fails the test. Right? So I will say that a test does not reject the truth, with probability 1 minus alpha if for every stochastic process of outcomes, right? Not just IID, regardless of the distribution of the process, if the expert prediction is indeed the probability of rain tomorrow given the past, if the expert gives the correct probabilities, then he knows he's off the hook. He knows that the probability that for some n, the prediction that he makes and the outcomes would be something that is specified according to our test to be a situation in which he didn't provide a good probabilities, this probability is small. Right? If this happens, we will say that the test does not reject the truth with probability 1 minus alpha. It means that if the predictions are the correct predictions, then there is a small probability of failing. Okay? And you should think about alpha as a small number. If the test has this property, then a true expert would be willing to sign the contract. Right? These tests have this property, right? For some small alpha, which I didn't tell you what it is. Right? Right? So the important thing is that for every stochastic process, the test should be such that the good expert, will know that he is off the hook. And the fact that the good expert is willing to sign the contract doesn't tell you anything about the stochastic process, because he will be willing to sign the contract for every process. And
you don't require to be markup or anything.
No.
And the prediction, is it reasonable to view it as a function from the past xi's to pk, or?
Prediction is a function. So prediction, the expert observed the rain and he update, right? And the expert essentially knows the distribution of this process, the joint distribution of this process, and he give you every day the conditional distribution of tomorrow given the past. This is the nice property of the test. Unfortunately, we have what we call the impossibility result. The impossibility result tells you that if the test has this property, that a good expert will be willing to pass the test, then a charlatan will be able to manipulate the test. A charlatan will be able to pass the test even though he doesn't know anything about the stochastic process. So this would be something similar to this. So this would be the impossibility theorem. If T does not reject the truth with probability 1 minus alpha, then for every epsilon, there exists a strategy actually, let me remove this for every epsilon. There exists a strategy
Only economists would call this bad news.
What? Even
Only economists would call this bad news.
bad news?
Saying from a machine learning point of view, it's
This is
actually
great.
an algorithm used to predict the future. That's
Yeah. Yeah.
it's accurate.
No, this
Passes
is only true if you're actually an academic, you call it great.
No, he's saying there's a good way to predict the weather.
Yeah. Algorithms are based on.
So there exists a strategy. What do I mean by a strategy? I mean a way to concoct probabilities. A strategy would be a way to concoct probabilities given what you said in the past and what actually happened in the past. So given what you say in the past and what actually happened in the past, you are going to randomize the number that you are going to give. Right? You are going to randomize the number that you are going to give, such that, and notice that this strategy is independent of the stochastic process that actually generates outcome. But this strategy would be good for all these processes, right? Such that for every stochastic process of outcomes, if predictions are randomized using this strategy, if the expert uses this strategy, if the distribution of pk is according to this strategy, so if, by that I mean pk is a number between 0 and 1 that is randomized using this strategy, right? So if the expert does not consult any crystal ball, he just tosses a coin every day depending on what happened in the past, then the probability that what's written here, right, for some n, the probability that the expert will see us again in his shop demanding to get compensation is small. Right?
Is it possible to reverse the quantifier to say that there is one strategy that will work for every test? Or
Yeah? No, of course not. No.
Exactly alpha, did the same alpha here?
Yeah, so that's why I was, in fact, to be a bit more accurate, I would have to say, for every epsilon, there is a strategy that gives here alpha plus epsilon. I actually don't know whether this is, as I wrote it, is completely true, but it's sufficiently small cheating, right? I mean, what I should have written is for every epsilon, there is a strategy that would give here alpha plus epsilon. I don't know if there is a strategy that would give exactly the same alpha. Even though for these cases there is. Okay, so let me tell you a word about how I interpret this result. For me, the expert testing literature, even though I appeal to this story about somebody giving you prediction about weather, right, which is essentially what Google Weather does, right? Google Weather, if you go to Google Weather, they don't tell you if there is rain. They tell you the probability of rain tomorrow. But it's not that the subject matter that I'm interested in is the market for prediction, right? What I'm interested in here, what I find most interesting here is that this is a way, the entire game theoretic environment is a way to think about the meaning of probability, right? What does it mean to say that the probability of rain is 50%? What is the testable implication of this assertion? After all, we don't actually see the probability. We just see whether there was rain or not, or there wasn't rain. And this test is a way to check whether probability matches what actually happens. And in a way, this theorem tells you that there are no testable implications for objective probabilities Because, I mean, whatever way you try to check whether prediction matches observation, there is some way to concoct the prediction that will match the observation always, right? It means that in a way there is no falsifiable implication for a theory that claims to know the probability of future events, right? Because there is a way to concoct probability that will never be falsified, right?
Except by another weatherman beating it.
Except by what?
Another weatherman coming along in parallel and making better predictions.
Another weatherman, well, that may be true, even though, I mean, so there is one direction in which this literature went that added another weatherman. Still, these two weathermen can still be passed the test together. So.
No, but the other weatherman could beat you just in terms of his accuracy.
Yeah, then you
Yeah.
can do a different test.
Yeah. So if there are two.
Very good ones.
But they can also cooperate together if they don't know anything and pass the test. So the main message will stay, right, with the other weathermen. Yes?
I'm curious about the following test. Over time, I ask you to predict 10 days where it's going to rain, and you get to choose which days those are, and then I pass you as long as it rains on all those days.
So again, can you...
So the test is that over like some amount of time, you get to pick 10 days on which it's going to rain, kind of for sure. Or
in which I claim that it's going to be rain?
and then you pass the test as long as it rains on all of those 10 days.
Well,
It's
the only...
not DNRT, because if it's always 50-50, always.
Yeah, if the truth is IID, half-half.
Maybe if you were willing to make some assumptions on the stochastic process.
Yeah, if
Right,
you make
so another direction in which the literature went is to make some assumption about the stochastic process.
The theorem is, how does it look? I've seen Percy Diaconis giving talk on this stuff.
So Percy and Diaconis, actually, I don't know. I don't know how it relates because I don't know which paper you refer to. This theorem, the way I know it is it's very similar to a paper of Olszewski and Sandroni. And this is from 2008 or later 2010. I don't know. I don't know about this paper of Percy. Diaconis, and maybe I will mention my contribution, which is not directly related to what I want to say more, but I will just mention it, that my contribution to this literature is to remove this assumption that we check the expert after finite time. So in my paper, the expert after we see the infinite sequence of prediction and outcome, we check then, right? So we have a wider class of tests, but still I show that every such test is manipulable.
So to follow up on Boaz's question, we can't have what this is saying is that once you reveal your test, you basically also reveal how to cheat this test. Mm-hmm. So what if one, and part of the reason is that these tests are supposed to be falsifiable. There is a proof saying I should be able to take you to take you to court if you're wrong, etc. If we just want to say, look, I want to see if this is a particularly good tester or not, I might have a distribution on the tests themselves, mm-hmm. each one of which is supported on things which are all DNRT. And then I could say I pick one of these at random, and the question is whether you can pass this particular one. How does that?
Then the theorem would stay as it is. Only the manipulated strategy. This is assuming I know how you are going to randomize, right? If you declare I'm going to randomize a test according to some probability, then we will have to. We don't even need to assume that all of them are does not reject with the truth probability 1 minus alpha. We just need to say that the expectation would be 1 minus alpha, and then here I will say that. With high probability, right? With high probability that depends on my randomization as an expert and on your randomization as a tester, and the probability would be small.
You don't lose anything.
No, I don't lose.
Know which of these 100 tests is going to be one random.
No, I don't lose anything by changing the definition of test from a kind of deterministic test to something that will say that given the sequence, I will give you probability.
The min-max doesn't work, so even though this is the case, you still can't switch the quantifiers and give a probabilistic strategy that will just work for all tests.
So I'm surprised by what you say. The min-max doesn't work. I mean, essentially what these theorems based on is that the min-max does work, even though it is infinite. I mean, you have to prove it, but...
Then there should be a probabilistic strategy that works for all tests, no?
Yeah, can't you usually min-maxes, you can switch the order of quantifier?
Yeah, no, the order of quantifier here between, this is one quantifier, the quantifier for every stochastic process, and the quantifier that there exists forecast that pass. So the quantifier that I switch using the minimax is this quantifier, the quantifier for every stochastic process, and the quantifier of existence of way to pass the process. The minimax that you are aiming at is something that would be a strategy that works for every game, right? The kind of things that you are suggesting to me. This cannot be, right? It's not the fact that you cannot have a strategy that works for every test has nothing to do with the infinite horizon. It is not true even in finite horizon.
The test could be tailored to this.
The test could be tailored to what happened. Let me give you an example, right? Suppose that I say that the probability is IID half-half. We can agree in advance that if I say that the probability is IID half-half, and 1,000 days we always see 0, 0, 0, 0, 0, we can agree in advance that I fail, right? Because it cannot be that we always see this. But we can also agree in advance on any other specific sequence, right? We can agree in advance that if this happens, right? These 3 dots are for some arbitrary numbers, right? We can agree in advance that if exactly this realization will happen, then I fail the test, right? Because
you're not deterministic. You're assuming here that the strategy, that the cheater, forecaster, is deterministic, and then of course you can cause him to fail.
No. Wait, I think
The cheater will just output 50-50, like I guess the cheater.
No,
in this situation, the cheater will output half all the time. I guess that's the.
I wasn't even talking about the cheater. I want to explain why we cannot change the quantifier between the tester and the strategy. Why it would not even be natural for the true expert. I mean, if we allow the inspector to declare the test after the fact, then...
No, not after the probabilities are set. I think what Buzz means, here you're saying after the probabilities of the tester was set, and you see everything, then declare the test. Then clearly you can not...
Okay, so what?
But what Buzz, I think, was suggesting is take a predictor. Don't set his probability. He says 50-50. It's not after the fact, but just have one test. It's not after the fact. It's just one predictor for every test, but it's not after the fact. Of course, after the fact.
You want that there would be a way to predict a strategy that will pass every test, right?
You want the strategy at some point to know what the test was. If not, it has to. At what stage does the strategy incorporate the test into account?
I am claiming that there cannot be a strategy that passes every test. In fact, I'm claiming more. Even the true expert cannot pass all the tests at the same time. He just can pass each of the single tests separately, right? He can pass, the true expert will pass each test with probability 1 minus alpha. But there will be some tests he will fail, right? That's what I'm claiming. I'm claiming that it's just too much of a burden to require the expert, either the true expert or the false expert, to produce prediction that will pass all the tests at the same time. Because there are so many tests, right? So even if you are passing each one of them with you are failing each one of them with very low probability, you will fail one of them.
What she's asking is if you had a bad strategy, could you pick before the game starts? Could you find SNPs for
Yes.
which you will fail? I think
Yes, you will be able, but you would be able to. Yes. So for every strategy, I will be able to find a test that will fail that strategy. Yes, and I will. And in fact, this is not as obvious as I was trying to do here, but I will say it in a moment when I will.
And might be able to pass all computable tests.
Well, good question. So let me move to my second part of the talk. So I have like... No, I'm not going to prove this theorem because I want to present something else in addition. But and because this is already an old stuff, right? It's maybe not 2010, maybe 2011, but it's relatively. And also the way I presented it is from Olszewski and Sandroni, not from my paper. So I don't talk about it. Okay, but this is the background that I need. And now I'm going to point your attention to the fact that I did two things. I gave you the example of the calibration tests. And in the example of the calibration tests, I actually wrote down the test. And I actually wrote down the manipulating strategy. I told you how to manipulate. Right? Here I didn't write it down, but I told you that I could write down if I wanted to. Here, on the other hand, the test is given just by any abstract set, right? And the manipulating strategy, I just told you that there exists a function, right? Usually in game theory, the way we model the intuitive notion of strategies by a function, but I don't think this mathematical creature actually captures our idea of strategy. I think a better way to capture our idea of strategy is a computable function, right? Because we actually want the expert to be able to produce this forecast, right? And I also don't think that just an arbitrary set captures our intuition of a contract. Right? The contract should actually be written in a way that we will be able to check whether some sequence of prediction and outcome violates the contract or not. After all, if the contract is violated, somebody has to go to the court with the contract and say, look, from the contract it follows that this sequence fails the expert. Right? So I'm going to talk about expressible inspections and computable strategies. There is not much to. Shit. Well, I will not use this. A contract is expressible if C is decidable, right? So if there is that's what I mean, that if there is a Turing machine that gets a sequence and tells you, and halts on every sequence and tell you whether the sequence is in C or not. This is what I would call expressible contract. And the reason I call this expressible is that I think about the contract as written in some formal language, right? And I want it to be the case that for every sequence that is not in the contract, there will be a proof, right? So there will be kind of a sequence of assertions that every assertion follow from the previous assertions that show that the sequence is not in the contract, or that the sequence is in the contract. Because I want the inspector to be able to go to court with the contract, with the set C, and with this sequence, and prove in court that the sequence is not in the contract. So the elements of the contract should be sequences for which there is a proof that they are in the contract, which means that the contract should be at least what's called computably enumerable, right? And I will make a somewhat stronger assertion, decidable. In fact, I only make this assertion, we only make this assertion in the paper because we thought it would be too much to explain why we want it to be computably enumerable, so people kind of accept the idea of decidable better. So, but it's a further restriction, right? I want that if the contract is violated, the inspector will be able to prove that the contract was violated, and also I want that if the contract was not violated, the expert, right, the forecaster, will be able to prove that the contract was not violated. So it's a rather strong assumption. This is what I mean by expressible. And a strategy is effective. Right, the strategy, I remind you, this is this, if it is computable. Okay, I don't know, is computable. I mean, I guess for this audience, I could just say, I could just call this decidable contract and computable strategies, because I don't feel I have to apologize so much for why I want that a strategy would be computable, right? It should be self-evident. I mean, if somebody has to concoct the probability, he has to have some strategy, some way to produce them, right? So it has to be computable.
Given an independent sequence of random coins, the way you.
Yeah. You are also given an independent. So what I mean here by computable, right? I think it's the same thing. So to say that this function is a computable function to distribution over 0, 1. Is the same thing, like I can produce this outcome if I'm also given a sequence.
The thing you produce, though, is also a real number, so
yeah,
it's represented as a...
Yeah, it should be represented. So yeah, this is a bit of a nuisance. Let's say that let's say that you know the story about this guy that discovered that square root of 2 is irrational and got thrown to the river for his trouble. Let's say that he kept this to himself, and that we live in a world without every number is rational, right? I guess yeah, every number is rational. Let's say that all predictions are rational, and
right, you're just joking, right? So you make some. Do you have some way to make this mathematically correct?
Yeah, I mean, I would just say that every time you see this thing on the board, what I mean is that is just rational number in this thing, right? What I mean is just rational number. Every time I wrote here this interval, what I actually mean is the interval intersection with rational number. And if you want, I can change here to say that I'm only looking at stochastic processes for which the conditional distribution is rational. For which the conditional distribution is always rational or always computable or something like that. Right? The only thing is that I don't have a way to say...
There is sort of complexities here with real numbers, right?
Yeah, I mean, and instead of rational, you could talk about computable real numbers. That doesn't, that's the same thing for me. Yeah. Still there would be real numbers that are not computable, and I have to say something about what happens if the truth is, if somehow God randomizes using real numbers that are not computable. So if we assume that this is not the case, if we assume that we are only looking at stochastic processes with condition...
It doesn't matter. Yeah, we don't want to spend too much time.
Yeah, it doesn't matter, but...
Approximated like with arbitrary precision. I should have asked. I take it back.
Surely it doesn't matter.
Okay, so I gave you a general theorem that says that for every contract there is a strategy that manipulates the contract, but I just say that that I don't think that what I called contract actually captures our intuition of contract, and I don't think that what I called strategy actually captures our intuition of strategy. And I gave you examples. This is the earlier calibration literature. And I didn't mention here names, but there are, in addition to Foster and Dvora and David, which I mentioned, there is Hart and Maskolel and Fundenberg-Levin, and there are many others that I don't even know. But there are many other papers that actually specified the contract, and these guys also constructed the manipulating strategy, the effective manipulating strategy. So there is still one thing to prove in the middle, and this is that every expressible contract has an effective way to manipulate, to be manipulated. This is unfortunately not the case. Right? So will you guys see if I write here? So I want to tell you about two theorems. Theorem 1, there exists an expressible contract C that does not reject the truth with probability y minus alpha. So for every alpha, there exists a contract that does not reject the truth with probability 1 minus alpha. But it doesn't have this property that you have a strategy that will pass the contract regardless of the stochastic process. I'm going to say that this theorem doesn't hold. So I'm going to take negation of this theorem. So it would be a cascade of De Morgan law. So, but for every computable F, right? For every computable strategy, let me not write exactly what is F. For every computable function F like that, there exists some stochastic process.
Computable?
Yeah, some computable.
Oh, I see. The stochastic process is actually computable.
Yeah, it is actually computable. And even more than computable, let me do something a bit more than I promised because of this computability. Let me say, and some n, number n, such that if predictions are made according to this strategy, then this doesn't happen, but I will prove something a bit stronger. Then the probability that before this time ends, so there is kind of a bound. I mean, I'm just, it's not much different than the negation, but I just want to emphasize that this is not going to proceed forever. At some time, the expert will fail. Right? The probability that at some time the expert would fail is 1. Or let me write it 1 minus alpha. Okay? With high probability, the expert will fail. So what does it mean? What does it say? There exists.
Really, I mean, the expert is going to fail with very high probability.
Yes.
Well, the truth is accepted with very high probability. Or?
Yeah, the truth will be accepted with very high. The truth is accepted with high probability, and the false expert will fail with high probability on some process.
When you say computable stochastic process, you don't mean that you can find that.
What I mean by computable, I mean that this is a stochastic process that can be generated by a Turing machine. I don't mean that I can find a stochastic process. Right? I mean, this is a property of the stochastic process. It has nothing to do with the test. I mean, this just mean, when I say this, I just mean that there is a Turing machine that with access to a stream of random bits that generate this process. So let's assume that God is using a Turing machine. Then there is something that God can do. There is some way in which weather can be produced such that if this charlatan is going to use this strategy F, then he's going to fail the test, and he's going to fail the test at some time. Right? So this theorem, in a way, reverses the impossibility theorem that I just showed. it's very related to two other papers with similar spirit, one of Fortno and Vora, and another of Al-Najjar and Sandoroni and Weinstein and Smorodinsky, and I will mention these papers in a moment. And this paper is in a way part of, part of my research ideology, right? I like this, I like adding these computability assumptions to all sort of game theoretic modeling, like the way we model the idea of strategy and the way we model the idea of test. And I like it especially when it overturns previous results, right? So this is one of these cases. Yes?
So I guess for this audience, another natural version would be when you replace the decidable and computable by efficiently computable.
By efficiently, yes.
So this is probably still to theorem one, right?
So this is actually the paper of Fortno and Vora that I mentioned. I will mention it in a moment. I will tell you what is known about adding efficiency. For me, the efficiency is less important. I'm more interested in this because I have this idea of if the contract is violated, there should be a proof that the contract is violated, right? So,
intuition, just so I understand, like it looks like maybe the intuition is that the contract will say you cannot use this computable strategy and you cannot use this other computable strategy. It just sort of enumerates all the computable strategies. This computable strategy will fail at n equals 1. For this computable strategy, you'll fail at n equals 2. And so you kind of plan it out and then...
Yes, so this relates to the answer that I was going to give to Yael, right? I mean, the intuition for this theorem is that the set of computable strategies is can enumerate. For every computable strategy, we will concoct a test that fails that strategy.
Like a subsequence of the natural numbers that is associated with that strategy, and you want to...
I don't think it can be done that way because I still have to make sure that the true expert will pass this test that says that, right? I mean, I still have to make sure that the true expert is going to pass the test. So I have to create these tests in a way that still control over the probability of the true expert to fail the test. And I have to create these tests in computable way. But essentially, this is just the idea that for every strategy, there is a test that this strategy, in one moment, that this strategy fails on this test. It's very obvious how to concoct a test that will fail a pure strategy. It's less obvious how to concoct a test that will fail behavioral strategy, right? Strategy that randomizes. That's why I couldn't give a quick answer earlier. So this is one thing. And this is actually something that was already done in the original calibration literature. So this is, for example, there is a paper by David that shows this. And essentially, this theorem is just saying that you enumerate over the computable strategy, and for each one of them, you concoct one test that fails this strategy, and you make sure that the probability of failing the test gets smaller and smaller in a way that a true expert will still fail all of them with small probability, any of them with small probability. Yes?
So when you do that, you probably get some restrictions on the probability. So assume we all knew that actually the weather is sort of independent from one day to another. We just don't know the probabilities, or maybe we know it's just a Markov process or something.
Suppose we know that it's IID. There is a very simple test, right? We will just look at the prediction that you make on the first day, and we will see whether it matches the frequency in the infinite horizon, right? If we know that if we know,
but I didn't say IID. I just said independent, not IID.
Independent also there is a test. It's less easy to construct, but there is also a test. There is also a manipulating test. The thing with independent process is that I'm not understanding the logic of your question. I'm not sure why you're asking it now. independent process, even here, if I would make the restriction of only looking at independent process, then this theorem would not be true. There is a test that...
I'm asking it the other way around. So when you construct the strategies, these probabilities, will this be very weird processes which produce a counterexample? Because maybe actually we know that the world is not that weird.
You say that when I construct this process, yes. So I
don't want you to construct super weird ones. So maybe I can't expect that they will be independent, but I sort of, the weather will not be governed by some very weird process. The weather in 5 years will not depend on the weather today, for example.
Are they actually going to be stochastic processes, or are these probabilistically going to be deterministic?
No, you can also choose them. The writing here stochastic process and writing deterministic is the same thing, because if there is stochastic process, then there must be some realization on which you are going to fail. I'm just writing it in order to look like this. No, so in our case, it would be a very horrible process, right? It would be specifying exactly the sequence on which it will fail.
So it will be not stochastic, it will be just deterministic.
Yes, I mean, I'm not sure that's what you asked. But, I mean, yeah, I mean, in our case, we can make it deterministic, but the problem is that it would be a very weird stochastic process, right? But this is because we started with the assumption that we want a test that passed the expert for every weird stochastic process, right? I mean, we want the test to be able to pass the expert regardless of the stochastic process.
Maybe what you're getting.
But, so my question is, assume we all have some prior, we all agree on that. Okay, so the process, we all don't know really what the weather is, but we all sort of moderate experts, so we all know it falls in a certain class of processes.
Yes,
What happens to this whole literature?
Yeah, what happens to this whole literature? Good question. This is actually an active area now. We don't know exactly what restrictions on the stochastic process would deliver this impossibility theorem.
I'm a bit confused now by this example that you mentioned of, if it's independent processes, then here's an easy test that works. So how does it affect this theorem after all? I mean,
then the restriction, the set of processes make two restrictions. It make restriction on the definition of don't reject the truth. We only want it not to reject the truth on a smaller class of processes.
Processes is first. So this whole theorem says fix a class of stochastic processes, and then if T doesn't restrict.
Yes.
Okay.
But we only know the theorem when the class of the stochastic processes is all processes. If you make other restriction of processes, for example, if you make a restriction of the process that it would be independent, then I know that this theorem doesn't hold, right? If you make a restriction that says that the process is Markov, then also I know that the theorem doesn't hold. I know that the theorem do hold if you make the restriction that the process is exchangeable process. I don't know what happens if the process is stationary. Yeah, it will hold. The impossibility theorem would hold. I don't know what happens with stationary processes. I mean, we don't know exactly. We don't have a good answer for which class of processes this theorem works and which.
The version of the theorem hold?
The computable, I didn't. So suppose I would look at exchangeable processes, and I will only want it to pass for computable exchangeable process, and I will ask that there would be
Probably we should go to theorem 2.
Yeah, maybe we'll go to theorem 2, and I actually think it will work, but I don't want to commit. Theorem 2, I just want to, what do you need? I mean, we already know that if you have an expressible contract that does not reject the truth, in fact, if you have, sorry, you had a question.
I think I figured it out, so you can
continue. We already know that if we have an expressible contract, there is some way to pass the to pass the test, right? Because there is a way to pass every test. And we already know that computable strategies are not going to pass you the test always. What will pass the test? Well, if C is expressible and does not reject the truth with probability 1 minus alpha, then there exists a strategy F. I don't know how to denote it. Strategy F that can call to an oracle that solves the halting problem, right? I saw it denoted somewhere like this, right? A strategy that can call oracle that solves the halting problem, but is not computable, right? That manipulates the test. So this is manipulates the test. I mean that such that for every stochastic process, if for every computable stochastic process, if pk are randomized according to this strategy, then the probability to fail the test is small. So if you are only interested in expressible contracts, as I am, then there are contracts that will not be able to, that an expert that cannot, that is restricted to effective strategy will not be able to pass. But if the expert, instead of knowing the true distribution of the process, has a way to solve the halting problem, then he will still be able to pass the test.
Does this pair of theorems climb up in the hierarchy?
Yes, so this would be...
Contract to be in pi 3, then you get something in sigma 4. That
yes, so or in general, if you have an expressible contract and you are allowed the expressible contract to appeal to some oracle, then you can manipulate the contract if you can call to an oracle that solves the halting problem according to that oracle. So let me mention a couple of papers that I think are very related. One paper, I think the first paper that introduced this idea of adding computability to game theory. I still have like 5 minutes. Huh? The first paper I think I know of that introduced this idea of adding computability to game theory is a paper by Rabin, Mikhail Rabin, in 1950, I think. This is in kind of all the annals of game theory that kind of conferences in game theory that I think were published by Princeton. I don't think the journal still exists, but it includes very interesting game theory papers. So this is Rabin. This is the idea of adding computability as a requirement of the very definition of strategy. And Rabin also gives an example of a game that doesn't have a value, zero-sum game that doesn't have value if you restrict player to play computable strategies. And essentially, this is what we have here. We have a game which the game itself is computable, but it doesn't have a value. Those of you who know the kind of the game theoretic thinking of this literature. The other papers I want to mention are papers from the expert testing literature. One is the paper of Fortno and Vora. So they prove that there exists a contract that, assuming that what they prove is, I will tell you exactly what they prove because I don't know if I can formulate it correctly by appealing to an assumption. They prove that there is a test that is polynomial, and such that if you have a strategy that manipulates the test, you can also use this strategy to factor numbers, right? To factor numbers. So in particular, if you have some assumption that says that you cannot factor numbers, then you cannot manipulate this test. And the other paper that is related both to our papers and also related to the kind of questions that you ask is paper by Al-Najjar and others, and also another paper by Olszewski and Sandroni. And these papers asks about restriction of the set of stochastic processes. Right? And I say that we don't know exactly for which set of stochastic processes the theorem holds. In our case, there is some aspect of this, because in a way, I didn't emphasize it so much, but all the stochastic processes that, at least the one that fails the expert, I want them to be computable. I kind of make an assumption about the way God randomized the weather, and the assumption is that God uses a Turing machine, right? The other papers make other assumptions, for example, that God uses a Markov process or that God uses an exchangeable process. We make here the assumption of computability of the stochastic process.
But you don't need, I mean, in your case, it's a thing saying it should contain all computable things. But
yeah, but I don't need, yeah, it could contain more, yeah. Right, in their case, it plays more on this issue that restricting the set, make this property weaker and make the demand that you want weaker. This doesn't play a role in my paper. Okay, thank you.